Yes, hi there everyone. Welcome to this webinar. Well, we'll present the research I've done during my research project at TNO Diana. And it was about random fields for nonlinear finite element analysis of reinforced concrete. I graduated in November at the TU Delft, and now I'm working at Royal Haskoning DHV, and I'm doing seismic analysis there for buildings in Groningen. And now I will give this presentation. Hopefully at the end of this webinar you will be familiar with the random field function, which is now available in Diana, and you will be able to use this function. I will hopefully give all the information needed to do so. So let's start. First I will introduce you to this subject of random fields. Thereafter I will give the information which comes into play when you apply a random field, and then I will show some examples of random fields in Diana. And then finally I will give the conclusions and you can ask some questions. Well, if we look to random fields, and I will give an introduction to this subject now. We will start by looking into a bridge, and if we look to this bridge from an engineering perspective, then we want to know the structural behavior of this bridge. For example, the deformation of the bridge or the failure capacity. And what's becoming more and more of interest is the probability of failure. And we talk about probability of failure because there are uncertainties in the analysis. For example, uncertainties in the loading and in the capacity. And in this webinar we will focus on the uncertainties in the material properties. And if we again look to this bridge, then if you look, for example, to the tensile strength, this could be a distribution of the tensile strength in the bridge. But it is unknown if we look to a certain bridge. This uncertainty, we have to deal with it. For example, this could be one distribution of the tensile strength, and it has a certain mean value and also a deviation. But this could also be a distribution. This is uncertain. And one of the approaches is that we use safety factors and calculate with a lower tensile strength in analysis. But the other option is that we take the spatial variability of for example, the tensile strength or any other material property into account in the analysis. And that's what we do with random fields. Well, how do we take the spatial variability into account? Well, first we are considering one position in the bridge, one location, and if we look to the tensile strength there, then we can consider this property as a random variable with a certain mean value and a certain standard deviation. And then we can characterize this, at this point, the tensile strength. Well, if we look down to a second location, then we have to consider two random variables which are correlated with each other. And how strong they are correlated with each other depends on the lag distance. That's the distance between the 2 points. But if we not want to consider only 2 points in the bridge, but we want to consider the full length of the bridge, then the concept of random field comes into play. And this is a mathematical description of any property, and it is has to do with the spatial variables and statistical variables. And there's a distinction which have to be made between the description of the random field as a mathematical concept and the realization of a random field. From the mathematical description, we need a random field generator to get a realization of a random field to do a calculation. And there are different random field generators to do so, and I've compared some of them, and I will show some results of that later on. And the different random field generators are also made available in Diana. Okay, now we will talk about the correlation function. This function, as I showed earlier, describes the correlation within the field. So here you see one correlation function which is quite used often in for concrete, and it's called exponential correlation function. And it's in the exponent you can see the lag distance and also the correlation length, which is denoted with LC. And below you see the graph, and on the x-axis you can see the lag distance, and on the y-axis you can see the correlation. So for small lag distances the correlation is strong, and if the lag distance increases then the correlation decreases. Well, the second variant is the squared exponential correlation function, and here the values in the exponent are squared, and this gives a quite other, the graph is somewhat different. And if we look to the realisation, which with those correlation functions, then we see that the one with the squared exponential correlation function is much more smooth. So values which are close to each other are more correlated than with the exponential correlation function. Okay, then we will consider the we now look to the correlation length, which is below in the exponent. Here you can see a realisation which is made with a correlation length of 5 meters, and if we decrease it to 1 meter, then we can see that the graph of the correlation function shifts to the y-axis, and the realisation of the random field fluctuates more. So with this parameter we can influence the realizations of a random field. And then another property which is sometimes used is the threshold value, and this comes from the idea that if we have one batch of concrete, then the material properties of that batch of concrete are correlated with each other with a minimum value, and this is the threshold value. In this case, the correlation between 2 points in a concrete beam is at least 0.5, and if they're closer to each other, they will be stronger correlated. So these are some properties which we can use to define the correlation within the field and to influence the realization of a random field. Okay, if we want to generate random fields, we have to know two things. First of all, we have to know the input of which we have to use for reinforced concrete. And second, we have to know which random field generator we need to use. So that's what we're going to talk about now. First of all, if we look to reinforced concrete, and for the steel part there's a small variation in space, so it has no use to use a random field for that property. A random variable is appropriate for these properties. If you look at the concrete, then there's a large variation in space. And if you look in literature, then different values are used for the correlation length or distribution type, whatever. And here you see, if you look in literature, then correlation lengths from 0.5 meter to 5 meters are found. Exponential and squared exponential correlation functions are used. The normal and log normal distribution type is used, and the coefficient of variation varied from 0.1 to 0.3. So quite large deviations, and this is still a work in progress. These values have to be determined more precise for in the future, so and then probabilistic analysis can be made with in more detail. But what I did is I took the values which are used which are advised in the probabilistic model code of the Joint Commission of Structural Safety, and here they use a correlation length of 5 meters, a threshold value of 0.5, and the mean and the standard deviation depend on the concrete class you choose. And all material properties like the Young's modulus and the tensile strength are linked to the compressive strength. Then I looked into some different methods to generate a random field, and I first characterized the methods, then I implemented some of these methods, and then I compared the performance of these methods, and I will show this process in short. First, I characterized the different methods in two classes. We can distinguish two classes. Class 1 is actually a combination of two models. First, we have to generate spatial correlated variables, and these generated spatial correlated variables are discretized in a certain manner, and this is done with the discretization method. And the class 2 methods are series expansion methods. For the first class, we first have to define a random field mesh, and this can be done independent of the finite element mesh. And for every node in this random field mesh, we can generate a realization of random variables on that locations which are correlated with the values according to the input values. And if we want then link this to the finite element model, then we have to do we have to follow a certain method, and these are the discretization methods, and we follow the shape function method where between those points linear interpolation is applied, as can be seen here. And then if, for example, an integration point is somewhere between those points, linear interpolation is used to give that integration point a certain Young's modulus or tensile strength. Okay, then we have the class 2 methods. Here the random field is built up out of all different spatial functions, and they are multiplied with a random variable, and then finally you will get a random field. Here you can see an overview of all the available methods in literature, and of all those methods I only looked to this one and implemented this one in Diana, because these ones were the most promising in my opinion. These are the covariance matrix decomposition method, the fast Fourier transform method, and the local average subdivision method, and they are all combined with the shape function method, which is the method I've shown in the past slides where the linear interpolation is used. And also looked into a class 2 method, the explanation optimal linear estimation method, but in the end I dropped this method and only looked to the first three. And I will tell shortly something about those methods. For more information I will recommend that you read my master thesis report or look on the internet for more information, but I hope with some little information you have some background if you use those methods in these methods in Diana. Here the first one, covariance matrix decomposition. The random variables on all the nodes are generated by a matrix multiplication where the matrix L is the decomposed covariance matrix, and therefore we can use stochastic decomposition or eigendecomposition, and the vector X is a vector with all standard normalized random variables, and all those values are for the mean value or mean value which is varying in space is added to these values, and this is the mean. Then for the fast Fourier transform method we first look to the discrete Fourier transform, and then we'll come to the fast Fourier transform. For the discrete Fourier transform, the random field is represented by a sum of sinusoids. The covariance function is first transformed with the fast Fourier transform, although the Fourier transformation to the one-sided spectral density function, and then it's inverted back, and then we get the random field. And the fast Fourier transform is actually just an improved version of the discrete Fourier transform where a fast Fourier algorithm is applied. And this results into two things. That first, the random field mesh and the discretization of the spectral density function are coupled. And also we have to select a power of 2 for the number of random field elements in the mesh. So you're a bit limited in how many elements you have to choose. Second thing is that the random field is periodic. So this results in a symmetric covariance structure, and this is solved by generating a random field which is twice as large and then only taking half of the random field. So you get the right covariance structure when you generate a random field. Then the last method I looked into is the local average subdivision method. In this method, a random field is obtained by a subdivision algorithm. The algorithm starts with a very coarse random field mesh, and for this mesh we generate a random field with the covariance matrix decomposition method, and thereafter we repeatedly subdivide every cell and ensure that the statistical properties match with the previous stage, and for this we use a variance function. And this can be, the process can be seen in the picture below. Okay, then I compared those methods, and I did this by specifying certain inputs, like the mean value, standard deviation, and the correlation function, and then with all those three methods, I generated a lot of random realizations of random fields, and then I compared the output, like the CPU time, and also if the input values match with the measured values in the output. And here you see an example of such a result. Here I used the squared exponential correlation function in 1D, and I generated 2000 fields, and I used a normal distribution type with no threshold value and a correlation length of 5 meters. And here you see the exact correlation function, and if we then look to the correlation structure of which is acquired with all the different methods, then we can see that they are quite close to the red line. So from this we can conclude that all methods are quite okay, or actually performing very well. Then I will show a second example where I used different input. Now I generated a 2D random fields, and I generated 200 fields with a squared exponential correlation function using a log normal distribution type and a threshold value of 0.5 and a correlation length of 5 meters. And here again you see the exact correlation function, and here you see how the correlation structure in the generated random fields. And here you see they deviate somewhat more of the red line. You can see that the fast Fourier transform is closest to the red line, so from this graph we can conclude that the fast Fourier transform is slightly more accurate. And this is something which holds in general, that from my research it was found that the fast Fourier transform is the most accurate method. The outcome of this assessment of random field generators was that all methods are appropriate, so all are also made available in the end, and you can select whatever method you like. But there are some limitations. The covariance matrix decomposition method works only well for small models. For larger models with a lot of nodes in the random field, the random field mesh, this method becomes quite slow, so I would advise to use another method. The fast Fourier transform method is accurate and fast, so I would advise this method. The only limitation is that you have to select a power of 2 for the number of nodes in every direction of the random field mesh. But that's, I think, has to be no problem. And then the last method, the local average subdivision method, performs slightly less than the fast Fourier transform method, but is quite okay. As I said, all methods are implemented and can be used. Okay, then I will show some examples of random fields in Diana, and hopefully then it will speak to your mind somewhat more. First I will show shrinkage of a concrete floor. First I will show results where no random field is used, and thereafter with a random field according to the Joint Commission on Structural Safety model code. And second I will show analysis where I did an analysis with a random field in one direction with on the 4-point bending beam. But first I will show you how you can use random fields in Diana. The Joint Commission on Structural Safety probabilistic model code is implemented in Diana as a material model. If you look on the concrete, in the material class concrete design codes, then you will find the JCSS probabilistic model code. You can select this one. Then you can edit the material, and in the first block you see that you can select which concrete grade you want, and also the type, if it's ready mixed or precast. And all the other values follow from the option you select, but you can also change the values if you like to do a parametric study or something like that. And second, you have to define the random field definition. First you can select the method you want to use to generate the random field. Next you can select the number of nodes in the random field. And then you can, for this method, you can select if you want to use Cholesky or eigen decomposition. And then you can select if you want to use the squared exponential correlation function or the exponential correlation function. And then you can select which distribution type you want to use, for example the normal or log normal distribution type. Then you can select if you want to use a threshold value, and you can choose your correlation width. And with all those parameters, the random field is defined and random fields can be generated. Other option is to define it with a dot and a DCF file. Here, for example, material 1 is given a Young's modulus and a Poisson ratio. And if we want to have spatial varying properties for the Young's modulus, we can couple a random field to this property in the DCF file. You can add a block random field, and here you can select again the random field method, how many nodes you want in the random field mesh, which correlation function you want, the correlation length, standard deviation you can select. And also below you can select to which material number you want to couple this random field, and also which material parameter, and in this case it is coupled to the Young's modulus. And then you can select whatever analysis you like. Okay, this is the concrete floor I've looked to, and here you can see the random field of the finite element mesh, and this is an example of how the random field mesh could be defined. I would advise, if you use the squared exponential correlation function, to use an element size for the random field between a half or a fourth of the correlation length, and for the exponential correlation function I would advise even smaller elements for the random field mesh. This will give the most accurate results. This is a mechanical scheme of the floor. Here you see that it is a concrete floor on the Winkler bedding, and there is a reinforcement placed in the floor. And due to the shrinkage load, it will shrink, and stresses will be the highest in the middle, and cracks will occur. And here you will see the results where no random field is used. The crack starts in the middle of the floor and will grow to the sides in a cross pattern. And as you can see, they are quite broad, and this is a problem because a lot of integration points are correct at the same time, which will often leads to divergence. And the idea was that if we use a random field, that this would solve this problem. So now we will use a random field where the compressive strength varies, as you can see on this slide, and the tensile strength varies, and also the Young's modulus varies. And as you can see, in the middle of the concrete floor there's a weak spot, and there also the cracking starts. And from there the crack grows to, again, a cross pattern, and finally also secondary cracks arise. And well, this gives us similar crack pattern but somewhat more asymmetric. So here you can see how what the result is of using a random field. And if we look to the total number of cracks during the analysis, we can get some insight in the how well how much nonlinearity is occurring during analysis. And the orange line gives the results of the analysis where no random field is used. And here you can see that at the load factor of 0.5 a lot of cracks arise, and then again at 0.8 again a lot of cracks arise. And this are two steps which are, well, in those two steps convergence is not reached, but the analysis continues. And if we look to the analysis with the random fields, we again see that there are a lot of cracks at first, but later on the crack growth is more gradual. So there was somewhat improvement in the numerical performance of the analysis, but it still was, especially at around 0.5 load factor, it performs quite poor. So it gives a slightly better performance, but we're not yet at that. Then I will show some the influence of the correlation length. Here you can see 3 generated fields for the tensile strength with different values for the correlation length. Now you will get some insight in what will happen to the generated random field and also the crack pattern. First we'll look to the crack pattern where correlation length of 5 meters is used. This is the same as we've seen earlier, quite broad crack pattern. And then we'll look to the second one where a correlation length of 0.5 meters is used, and here the cracks are localized somewhat more and also in a quite realistic pattern. And then when the correlation length is decreased even further, a more diffuse crack pattern occurs, which is not realistic in my opinion. So I think a value between 0.5 and 5 meters will be more appropriate. Okay, now we'll look to the second example. Here I did an analysis of a 4-point bending beam, and here you can see the model. There's reinforcement at the bottom, and it is just a 4-point bending beam. And here you can see the random field which is generated for this beam. It's a 1D random field, and the tensile strength varies. And if we then look to the results, the shear crack now occurs at the left-hand side. And here you can see the force displacement diagram. And if we then look to a second analysis, then the random field has another weak spot, and the shear crack occurs at the right-hand side, and the force displacement the graph is slightly different at the ultimate displacement. Then for a third analysis, the shear crack developed at the left-hand side, and for the fourth, it developed at the right-hand side. So you get the asymmetric failure mode, which is quite nice, I think. So in this way, we can do hundreds or thousands of analyses, and we can do Monte Carlo simulations to get insight in the probability of failure or the difference in displacement or some other values. So this could be quite interesting in the future. So this was the presentation. The random field function is, I've presented a random field function, and this function can now be used in the YANA. And we have implemented the Joint Commission on Structural Safety probabilistic model code, which can be used. And random fields can be used for any other property in the program. For example, the thickness of a plate can be coupled to a random field, or other properties. And an integrated calculation of probability of failure is under investigation and may be expected in the next version. So then it will be coupled to a probabilistic model of Thank you for listening. I hope you enjoyed the webinar, and we'll be able to use random field function in the future.